All right. Welcome back, everyone. Today we're going to dive right in. First thing I'm going to do is give you a little bit of OS history, because everybody should have a little bit of OS history. And then we're going to dive in and start talking about one of the key ideas that will take us through the term, which is a process. And we're going to have to learn a few things around it in order to do that. So if you remember from last time, we actually asked ourselves what's an operating system several different times. And I don't know that we really came up with a full answer yet, but the idea was that there's hardware and there's applications, and the OS is somewhere in between. And here I've got its special layer of software that provides application software access to hardware resources, and it's a convenient abstraction. It gives protected access to resources, gives you security authentication and ways of communicating. But that's a lot of very high-level stuff. There was also this from your book, which is kind of your book's view of what an operating system is, and I think the fact that it comes up with these three pieces is pretty interesting. On one hand, it's a referee, which is making sure that things that are executing don't misbehave and don't violate things like privacy and security and so on. The other is this idea of the illusionist, which is programmers don't want to worry about finite resources. They want to think about infinite resources, or they want to think about things that are unrestricted in some way. And so the operating system provides a virtual machine abstraction to help us along with that. It's much cleaner than the hardware typically. We'll say more about that as we go on. And then the idea of the glue, which is this common libraries and other useful functionality like file systems that you really need to glue applications together, and the operating system implements them once. I mean, why implement the same thing over and over again when somebody can do it once and debug it and provide it as a service? Okay? So these three things, the referee, illusionist, and glue, I think is a very good way for us to start with what is an operating system. And today we're going to really dive pretty much into a combination of the first two. We're going to look a little bit at, we're going to start with the illusionist view of more processors than there really are, and then we're going to put a referee in there to make sure they can't mess with each other. So the other underlying theme, which I just started and which I'm going to hammer on all term, is this notion of software complexity. And these, I ought to see if I can find an updated version of this, because this is pretty old, but this is almost a Moore's law growth in number of lines of code in an operating system. And that's a little scary when you think about trying to make sure it all works. Okay? And so a lot of what the operating system is trying to do is, even though it's got this increased functionality, it's supposed to put it in a framework to help make sure that it actually works properly. Okay, were there any questions left over from last time about this? Okay, so the other final thing was, it's all about programs, and so we sort of talked about this notion that on top of the OS hardware virtualization layer is a bunch of things like threads and processes and address spaces and files and windows and sockets, and these are all the abstractions we're going to talk about throughout the term. In fact, today we're going to get three of them. We're going to get threads, processes, and address spaces. And then the software is somewhere other. And of course, in reality, the software's got to be somewhere, so it starts on the storage in the system somehow, and it gets loaded into memory before it can be executed. And so this idea of the software that floats in space is really not entirely true. The software is actually stored somewhere in in your system on a flash card. It's stored on the disk. It's stored in the cloud, whatever that may be. And the process of loading it into memory makes it suddenly an executable thing. Before that, it's just a program. When it gets loaded into memory and linked up with the operating system and made to run, now suddenly it's an entity in itself. It's running. Okay, and that's a big difference between the potential of not running yet and the thing running. Okay. So what's interesting about operating systems is it's gone through many phases. Now, it used to be in 162, we actually spent a whole lecture talking through several of these things. But I did want to say a little bit about them anyway. So the three phases which are particularly interesting is sort of this phase where the hardware was it. You had these big rooms, you had these tape drives that were going back and forth, and the flashing lights, and, somehow the romantic B-rate science fiction movies we all love all have those things in them somehow, right? These really big machines that fill rooms. And by the way, they still do have machines that fill rooms like that, but they're a lot more powerful. But the idea was the human was serving the machine. And a lot of the work that was done in the operating system was really trying to make sure that you never wasted cycles, because heaven forbid this thing was so expensive, if a human did something to waste cycles, fire them. Right? Why waste cycles? Okay. Then hardware started getting cheaper. And we started getting PCs and workstations, and GUIs started showing up, windowing systems with mice. And now we've got kind of this interesting point where the hardware starts getting so cheap, and now the humans, we got to make sure they're doing the right thing and not wasting their time, and therefore we're going to burn some hardware to make it good for the humans. And then finally, today we've got hardware that's so cheap we've got processors everywhere. Okay, my car's got 100 of them. Your cell phone's got several. Everybody's got Bluetooth devices and so on that all have processing in them. And this is really interesting because it is all about making it convenient for humans, but boy, this is chaotic and things are complicated, and really we've got to manage this complexity, okay? And so, here's a machine, okay? And you can see lots of interesting things. You got these old tape drives in the background that are moving back and forth, reading and writing. You got people sitting at consoles sort of submitting jobs. Used to have disk drives were the size of washing machines, okay, and you put a big disk pack in it. It's pretty hard to believe. I should have brought a picture of those. And it is very funny that this is a real quote from the founder of IBM, who once said, "I think there's a world market for maybe 5 computers." Okay, and you got the impression he was stretching his estimate. Okay, and of course, it's interesting that he was often called the world's greatest salesman by the time of his death because IBM became such a powerhouse in the computer industry, but it is interesting to see how off base people could be, right? You got these huge machines, heaven forbid, nobody else, who else could need a computer except for maybe the biggest countries or something, right? And so here kind of in the middle is an interesting sort of thing by Xerox PARC, where you started seeing windowing systems. And by the way, if you think that Microsoft invented Windows, or you think that Apple invented Windows, or you think that Google invented Windows, no, right? It was Xerox PARC. Okay, don't forget that. And they actually, that was a research lab for Xerox, and they were the first ones to come up with this idea of using Windows, which is interesting. And then today, this is just a shot of some kid's bedroom with, he's got a dinosaur, but then he's got like several different pads, and there's all these little portable phones and remotes and a Wii controller and this and that and the other thing. And boy, are we in a different space than on the far left there, okay? It's a pretty exciting time, I would say. So the rapid change in the hardware leads to all sorts of changing operating systems. So we started with the batch processing. We went into multi-programming and time sharing and graphical UIs and then ubiquitous devices. And basically, features that used to be in the big machines slowly worked their way into the smaller ones. And today, what's kind of interesting is if you look at the extreme small size, the little tiniest devices that we're spreading around our infrastructure are kind of like the big operating systems of the day, okay? And we're in a situation where a small OS is 100,000 lines and a big OS might be 10 million lines or more easily, and browsers are 5 million or more lines of code. So that's a lot of lines of code to get correct. Okay. And what's kind of interesting is if you sort of do tracing, let's do some OS archaeology. Okay, presumably you're not taking out your little hammer and chisel and whip it and chopping away at the web browser, but you could look. There's Multics, which was a big project at MIT, and it basically sort of begat AT&T Unix, and then BSD and Ultrix and SunOS and NetBSD. There's a definite line there. We had Mach and BSD kind of led to some interesting things when we basically had the original split off from Apple to Next Step and so on, and then came back to Apple. So that was an interesting sort of scenario, and Steve Jobs did that. And then we had Linux sort of begat Android, and then we had a bunch of operating systems that you probably have never heard of, like CP/M actually led into MS-DOS, which led into the whole Windows line. And then, of course, many versions of Linux. So the thing is that operating systems are so complicated that almost nobody ever starts from scratch with them. They all modify the previous one. And in some cases, when we talk about features in the operating system, it's going to be legacy features that are there just because they're there and nobody wanted to change them. Okay, and so some of the mess that we run into in operating systems and the complexity that makes them hard to get right, is all about their history. Okay, sorry about that. Boy, it looks like I'm going to be doing that once per lecture here. Okay, so let's see, did I lose my... Oh, this guy was not up there. Okay, well, I had a nice picture. There we go. So what's kind of interesting is here's this sort of trace through the history, and Multics was a very big project at MIT. And what's interesting is all the features in Multics have found their way into little handheld devices these days. And so as the power of the processors keeps getting stronger, basically, we put all of these features down until today. Basically, my cell phone is running features that are very much like the OSs of way back when that filled rooms. Okay? So that's why we talk about these features. So things like multitasking, protection features, virtual memory, all of these things are in little devices today. Okay. So what we're going to do for the rest of the lecture, that's my very quick brush through history, unless somebody had a question on history. One of the things I did forget to put in, and I will do this on the final version of the slides, these are already uploaded, but I'll put a new version up. What does it mean to have a core dump? And where the heck does that term come from? Anybody know what is core? Yeah.
When a process crashes, so all the data that process was using is stored somewhere, so you can presume where it crashed.
Okay, good. So when you hear about a core dump today, it says we take all of the memory state of the thing that was running and we store it on a disk somewhere so you can look at it and debug. That's a core dump. What is core? Other than sort of a piece of an apple. Huh? Nope. Doggone, I should have put this picture in there. Core is a type of memory. You have little tiny magnetic domains that actually look like lifesavers, and they're woven into a MET. Okay, and the way that these big computers used to work is they would store their data in cores where every little lifesaver-like round iron core was a bit. All right, and you got these mats of bits, and a core dump was literally taking what was in core, which was the memory, and putting it on disk. Okay, I'll bring a picture next time. I'll show you, but it's hard to believe that now that we have memories made out of DRAM, out of CMOS or whatever, that ever existed that way. But that was the way they stored data. Okay, so now you know. At parties. See, by the way, one of the things is when you finish with this class, you'll have a lot of great things to talk about at parties. But now you're coming up and you say, "Oh, guess what I learned in class today? You know what it means when it's a core dump?" And maybe they'll tell you, "Well, do you know what a core is?" And you can tell them what a core is. Okay, so just you watch for it. I'm going to give you these party tips. You guys will be wonderful at parties. It'll be amazing. So today we're actually going to have 4 fundamental OS concepts that we're going to talk about. Okay. We're going to talk about threads, which is a single unique execution context. We're going to talk about address spaces with translation, which is basically a chunk of memory that's being used by a thread. We're going to talk about processes, which are ways of packaging threads into a protected context for execution. And then we're going to talk about hardware features, dual mode operation, and the protection we can get from it as a way of making sure that processes can execute securely. Okay, so that's a bit of a roadmap for today. All right? And you can imagine that in conclusion, we'll come back to these 4, hopefully. So the bottom line of operating systems, as we've been saying here, is basically to run programs. And so basically, you've got somebody who enters a program, okay, and you've all started using C now, if you hadn't done before, right? How many people love C? Okay, there's a few of you, all right? So basically you write your program. It gets compiled by a compiler. The compiler produces an executable. A.out, for instance, is the output of the compiler. It's got some instructions in it. It's got some data in it. The net result is a thing that goes through the loader as well to produce this actual program. And then when we load and execute it, it gets into memory, and suddenly we have something that can actually execute. Okay? And part of this loading to execute is obviously getting the instructions and data from the original program put into memory. But look at this other stuff. There's a heap. There's some stack. Okay? And then, of course, in the same memory, presumably, there's an operating system as well. And then once we've sort of done this loading and set up the stack and set up the heap, then we transfer control to this, and it starts running, and suddenly, poof, we've got a running program. Okay? And it becomes a process, as we'll see later. And we're going to provide some services, so the OS might give it access to the network, it might give it access to file systems, and so on. And one of the key ideas here is, okay, yeah, we're all in service of the program, but we want to make sure the program can't screw up or compromise the operating system in any way. So the OS is basically doing all of this while at the same time preventing that program from compromising. All right? And oftentimes when we talk about viruses or we talk about interesting things in the news, Target getting compromised and so on. What we're saying here is that this level of protection that the operating system is supposedly providing has had a failure of some sort. Somebody's figured out a hole. They figured out a way around the protection. And so today, by the way, I want to give you a beginnings of understanding what type of protection ought to be in there. Not with the intention of teaching you guys how to hack into credit card systems, but I want you to start to see some of the ideas of what it is that has failed by knowing what was supposed to work. So somebody tell me, what are heap and stack? What is the stack? It's a 61C thing. Go for it. Yeah, so it's where we store the local variables, and also when we do recursive calls, we make a call with a call with a call. Each instance of the recursive call has another stack entry. Okay, we talk about pushing the stack and popping the stack. That's good. So notice that the instructions and data, the executable, really are like a proto-application. They're not really doing anything yet till they're loaded into memory. They have some state in the stack. They've got a heap, and they've got some data in registers, and they've got some hardware ready to execute. Now, suddenly, they're an actual entity that's running. So what's the heap? Malloc, yes. What is malloc? Memory allocation, yeah. So when you execute malloc, and you say, I want a block of memory, you're actually getting a block of memory off the heap. And notice these arrows are important for a little later in the discussion. Notice that the heap goes in one direction, so we start with an empty heap, and as we add more and more things, the heap grows and grows and grows. We start with an empty stack, and as we execute procedures and recursive procedures, the stack kind of grows and grows and grows. And notice how the two of them are growing together. Why? There's a hole in the middle. Why is that useful? Yeah.
Because we don't necessarily know how deep the stack or the heap are going to flow. So by having that space in the middle, we can use the empty space for whichever one goes faster.
Exactly. We don't know. Certainly the operating system doesn't know. Maybe you as a programmer know. You checked your program horoscope in the morning and you know exactly how much stack and heap you're going to need. But most people are not really sure, and the operating system certainly doesn't know how much heap and stack it's going to need. So the important thing is to leave a hole in the middle, and these two things grow together. All right? And that's how we make sure that we have the potential for growth. And this hole in the middle here is actually going to be kind of an interesting thing. It's important. Okay? Any questions on this? All right. So, and of course, obviously, among other things, there's registers in the processor. We'll get back to this in a moment. But for instance, the PC is pointing at the current instruction that's ready to run and so on. Okay, so that's going to get back to 61C pretty soon. How many people took 61C a year ago or within the last year? Good. How many of you took it more than a year ago? How many people took it 5 years ago? Anybody? Ooh, okay. But you remember everything from that class, right? So, fortunately, we're only going to need a few things from 61C today, so I'm going to tell you one of the things right now, which is the instruction cycle. So what actually happens when a program's executing, okay? And by the way, until we really make the distinction of what's a process and a program, I guess I don't want to say the process is executing because you don't really know what a process is yet. So when I say program is executing, I'm really talking about something that's loaded and actually running, okay? And I'm going to confuse you a little bit, and then we'll clear it up when you finally have the terms. We can clear it up because otherwise I'm going to be tripping over myself for the next half an hour. But what we've got is typically a processor is a piece of hardware. It's got a program counter, and that program counter points to some memory address, which is the next instruction that has to run. And that instruction basically is a set of bits that say what to do. Add two things together, store from memory, load from memory, etc. And what the processor does is based on the PC, it loads the next instruction and decodes it. And then meanwhile, that decoding maybe pulls two things out of registers. So for instance, we're going to add, we pull two values out of registers. We add them together with the arithmetic unit. And then the result maybe goes out to memory or comes back, and then the result of that is potentially stored back in registers. So this idea of executing is really that we pull an instruction out of memory, we decode it, we do something with it, maybe adding a couple of things together, we store the result back, and that was an instruction. Okay, and then we go on to the next one. And so at that point, we basically compute the next address, and we pull the next instruction out. Very simple idea. Okay, and so, for instance, we could look a little further about this. So here is some memory at the right, and I have addresses from 0 to 2 to the 31st minus 1. Why is that? Good. And what's 2 to the 32nd minus 1? Okay, good. So if we're dealing with a 32-bit processor, this would be the maximum size of memory, the maximum byte. So here is the hardware. Notice the lovely pink color. And our execution sequence is fetch an instruction at the PC. So wherever the PC is, grab it, decode it, execute it, maybe using registers, write the results back to registers or memory, compute the next PC, program counter, and then, poof, repeat. Okay? Cycle and repeat. And so what you see here is, we're executing, the PC is moving along, dump, as we go. Any questions? Okay, that was a pretty easy piece of 61C, right? The important things to note here, though, is that the state of the thread, or whatever is running here, I'm going to call it a thread the next slide, basically depends on a combination of what's in the registers, which is a bunch of integer registers and floating point registers and a program counter, as well as all the stuff that's in some memory somewhere. And together, that's the state of the running program thing. Okay? Everybody with me? So by taking all of those things together, which is a combination of both the registers and the memory state, that's what the current state is, and each instruction execution sort of advances that state somewhere else. And so when we start talking about virtualizing this, we're going to have to make sure that all of the state that is representative of a given thread, I should throw that word out now just because we're going to go to it next slide, basically ought to be kept track of in order to make sure we don't screw up the execution. Okay. Now, so the first concept we've got here for today is threads of control, and it's basically a single unique execution context. Program counter, registers, execution flags, stack. I should have put also plus all the state and memory that matters. Okay, and basically a thread is executing on a processor when it's resident in the processor's registers. So the fact that this thread has a program counter pointing somewhere into memory and the register state has been updated over time means that that thread is actually running on that processor right now. And if we were to take those registers and destroy them or save them in memory or something and stop executing from that PC, suddenly that thread is not running. Okay, very simple, but I just wanted to sort of overstate the obvious, okay? So the program counter holds the address of the executing instruction in the thread. Certain registers hold the context. So for instance, there's a stack pointer register that points in memory to where the stack is. There's a heap register that points in memory to where the heap is, okay? And so basically when we're allocating off the heap with malloc, or we're pushing and popping off the stack, we're basically moving the values in those registers that are pointing in memory, okay? And by the way, this is different for all different processors, so you don't have to worry about that now, but every, x86 is a little different from ARM, is a little different from all the different ones, okay? And registers basically hold the root state of the thread. The rest is in memory, okay? Are there any questions? Yes?
If you have multiple programs running, what keeps track of the different PCs?
The operating system. That's a great question. The question is, when you have multiple things running, who keeps track of all of this? The operating system does. And that's what we're going to be talking about by the end of the lecture. That's a good question. Okay? So, let me talk about the address space. This is the second major idea we need today. And basically, you could say the address space is a chunk of memory that's available to a thread. And we're going to virtualize that in a little bit. But sort of, if you think about all the addresses from all zeros to all Fs, those are basically somewhere in that address space. And so you could say it's the set of accessible addresses and the state associated with them. And so for a 32-bit processor, there are 2 to the 32nd bytes. How big is a byte? What was that? 8 bits. How big is a bit? A bit is a 1 or a 0, right? So the bit is a single state. You put 8 of them together, you get a byte. Okay? We're going to try, you guys are going to have all sorts of interesting terms, hopefully by the end of the term, but I'm hoping that one is one you already had. So what happens when you read or write to an address? Well, what's going to be interesting is it could be a lot of things happen. You might say, well, obviously you read the data that's there and you store the data that's back. But by the end, hopefully you'll be able to realize that perhaps nothing happens. Maybe it acts like regular memory. Maybe it ignores the writes. Maybe it causes an interrupt because you're not supposed to write it and it's read-only memory. All sorts of interesting things could happen. But the address space of a given system or process we're going to get to eventually is basically it's the whole set of addresses and the data in them and the behavior that you get when you read and write from it. Okay, and that will be a process's address space, or we could think of it as a thread for now until we get to processes. So in pictures, you could say, well, here's my address space, the program counter is pointing at the instruction, the stack pointer is pointing at the stack, etc. All right? And so we just went through what's in the code segment. So the code segment has all the compiled instructions from your program. The data segment sort of typically has all of the statics that you might put in your program. So in your C program, which you guys all said you love C now, at the top you might say some static variable, char star whatever equals, and then give a string. That's static data that's never going to change, and it's compiled into the program. Okay, so those static data are in the static segment, and then you have the heap and stack segments. Stack segment we already talked about. Heap segment we already talked about. So basically the address space is the container for all of these pieces we've already talked about. Okay? Now, here we come up with the question that we just asked a little bit ago. What about multiple threads? Okay, so we said earlier that a thread is like a single execution context. And if we have a bunch of processors, this is all very easy because maybe we have memory with a bunch of individual programs loaded in, and each processor is independently working on each of those programs, and so we're good to go. All right, that's not a problem. Hopefully not conceptually complicated, right? We've got multi-core. If it's got different processors, each processor could be pointing at a different thread, and we're good. Is everybody with me on that? What's tricky, and where we ought to go with this, is you typically don't have as many processors as threads. Okay, and in fact, in the extreme case here, if we said, well, the thing on the left is really only one processor, but we're going to make it look like it's a whole bunch of them, that's the good place for you guys to think right now. Forget multi-core. What if we only have one processor? Now suddenly we have to fake it out as if we've got a whole bunch of processors, and that's where we come into this interesting question of who manages this. Okay? And so that's where we're going to go right after Administrivia. Are there any questions? Okay, so hopefully everybody has started homework 0. Okay, if you haven't, you need to get in your time machine, go back in time to the weekend and start Project 0. I would say it's very important to get going. So I actually have a little bit of a story. So I actually decided to try to install VirtualBox on a machine that I had, and I already had VMware, a different virtual machine installed, and I put VirtualBox in, and suddenly my network was gone, and I couldn't figure out how to restore it and had to go back to a checkpoint. None of you will have to worry about this, I doubt, because you probably don't have as complicated as configuration as I do, but keep in mind that you want to give yourself lead time on installing things like this because problems always show up. Okay, if you think that you're going to go in and do the homework on Thursday night, you might have a surprise coming, and I'd prefer that you didn't. Okay, and that's not because the homework's hard, it's because the homework may not behave the way you expect it. So I would say you should get going on it. And that's why we have a homework 0, is so that you can iron out all of these funny details before you have to do real details. Okay, and I will tell you, the only way I fixed this was I actually had to go back to a previous checkpoint of my system to get it working again, which was a little annoying. But anyway, say la vie. Yes?
To do Friday at midnight or Thursday at midnight?
Friday at midnight. Now, one of the things that I think I'm going to start doing with the TAs, maybe I'll do this, maybe we'll make things do AOE so they're not confusing. Everybody know about AOE? What does it stand for? Nah. I knew I'd run into something like that. No, it stands for Anywhere on Earth. So the trick is when we make something do anywhere on Earth, so if we said Friday anywhere on Earth, it says as long as it's still Friday anywhere on Earth, it's still not due. I think we're going to start using AOE because it's basically either 5 or 6 in the morning Pacific time. For this one, it's really due midnight, but maybe in the next one we'll start making things do AOE. Is everybody up for AOE? The bad thing about AOE is it encourages you to not sleep, which is not something I really should do. The good thing about AOE is there's never a confusion when it's due. Okay? So how many people think it would be okay to do AOE on things? Okay, how many people would hate AOE? A couple of you? Boy, it's 50-50. I don't know. So those of you that would really hate AOE could make it do the midnight previous. I don't know. I'm going to talk with my TAs about it. But anyway, the answer of this one is this is due midnight Friday. Okay? And what you should really do is turn it in earlier and then go out and have a really good dinner and watch a movie. And I know. Students don't do that. But you should be going to section already. Okay? Last week was a good example of sections where they started helping you with infrastructure. You want to make sure you do that. I think the section notes are posted on the website. So if you're not going to section already, you should be. The other thing to note is that group sign-up form is going to be out next week after the drop deadline, which is, I believe it's Friday. So you want to get to finding your groups as soon as possible, okay? And then we'll have a sign-up sheet possibility next week. Okay? And we want 4 people in a group. Questions? Okay. So upcoming workshops on Git. So apparently hackers at Berkeley are actually offering some interesting stuff for people. If you go to there was an announcement on Piazza, an instructor note. How many people saw that? Did you see it? Okay. If you didn't see it, you should be able to find it now that you know it's there. But basically there's a link to a Facebook announcement that sort of talks about them. And there's both an introductory and an advanced course. And any of you that are thinking about doing systems work in the future, Git will be your friend. Okay, I love Git. but it takes a little bit to get. It's a little confusing at the beginning, and so these kind of workshops might not hurt. The other thing is I have office hours, and I haven't quite finalized these, so I know I had a couple of people query on Piazza about them, and I'm a little bit hesitant because we're still trying to stabilize the office hours for the TAs, so it might be either 2 to 3 or 1 to 2 or something, so watch, and I will put out a formal announcement when I'm really ready to make this go, okay? And that'll be in the next couple of days. We just have been kind of getting the infrastructure going. And if it turns out that the hours that we pick really don't work, I can figure out something else as well. The other interesting thing that was a posting on Piazza, which you may or may not have noticed, and I thought I'd point out, is if you go to the projects link and then you click under resources, there's actually a pointer to online textbooks. And I mentioned this last time, but I wanted to really point this out. As long as you're on campus and you have a campus IP address, you can actually read all of these for free. And so far, and these are like the O'Reilly books, you know, the little animals on them, and we actually posted one on Git, and 2 of them on C, and I don't know, we may post a couple of other ones, but these are great resources, okay? The O'Reilly books are fun. They have a cute animal on the front, which I guess is a good thing, but they're a good way to get into a given topic for you, okay? And so I suggest you take a look. And they're basically pretty much offered to... you know, as long as you're on the Berkeley net, and there's all sorts of other interesting books that are available. So you should take a look there. And I'm going to post a few others when we get going. The other thing that I wanted to point out is we're actually webcasting. Woohoo, I guess. So, you know, as before, this is actually posted on both iTunes and it's posted on YouTube. And if you just go to webcast.berkeley.edu and click on CS department, you know, computer science department, you'll see 162 listed toward the top. It's like the second line. But anyway, we'll put an actual link on the website soon. But webcast is not really a replacement for coming to class. So I hope you guys all come. You know, we get to see your friendly faces. The TAs get to see that you're here for part of the participation grade, so that's always useful. So view webcast is a great resource for studying and, you know, for the occasionally missed class, but I would not try to have a steady diet of webcast because, by the way, it's much nicer when I've got people asking me questions and stuff. It's sort of more fun from the front here, too. So, all right. The last thing I wanted to do administrivia is explain the collaboration policy again. So we sort of talked about things that are probably okay and things that are probably not. And just to point out that we're going to be, you know, using various tools to compare project submissions and so on. And so just be careful what you do, okay? Do your own work and you'll be great. Okay. Questions on administrivia? Oops. Okay. All right, let's dive back in. So how do we give the illusion of multiple processors? That was kind of a question. So we want to have this sort of idea of virtual CPUs on a shared memory. And assume we only have one processor. Now, I realize we talked a lot about multi-core last time. I mentioned it earlier in the lecture. But for now, forget multi-core, go back to one processor. And if we can figure out how to use one processor, then using more than one processor is going to be easy. Okay? And so assume a single processor. So how do we provide the illusion that lots of things are happening? And basically, we're going to multiplex in time. So let me explain what this picture really means. We're going to provide the illusion that we have several threads or processes. We're going to make that distinction a little bit. Say threads for the moment, all sharing some memory, and they're all executing as if each one of them had their own CPU. Okay? And we really want to do this in time, so we run a little bit of the pink one, a little bit of the blue one, a little bit of the yellow one, a little bit of the pink one, a little bit of the blue one. And if we do this multiplexing well, we could have the illusion that those are being executed on different processors without necessarily having to have more than one processor. Okay? Is that clear to everybody? Now, of course, if we do this poorly, we're going to screw everything up. All right? Because if we mix up stuff from the pink one with the blue one with the yellow one, it's just not going to work. Okay? We're going to get garbage out, and that's not going to be good. So we got to somehow do this well. And each virtual CPU clearly needs a structure by the operating system holding things like what its current program counter is, its current stack pointer, its register values, and so on, in order that the operating system can kind of swap in and out these pieces of data to give us the illusion that we have more than one processor. Okay? And how do we switch from one virtual CPU to another? Well, we take the current one that's running, we save the PC and stack pointer and registers in some state block somewhere, we load the PC stack pointer and registers from a different state block, and we go, and now we stopped running pink and started running blue, and stopped running blue, start running pink, yellow, and so on. Okay? Questions? Yeah?
Does anybody build the operating system where it's like hardware that runs in parallel so that those can switch faster?
Yes. So the answer to your question is yes for multiple reasons. So first of all, multi-core, as I just mentioned, there really are more than one processor, and so you don't need to switch. However, a more interesting answer to your question, I hopefully we'll get to by the end of the lecture, I'm going to show you something called simultaneous multi-threading, or what Intel decided to call hyper-threading, because why name something the same thing that somebody else did? But which will do what you think, or what you want it to do, and I'll show you that in a little bit. And that's actually hardware switching, but let's ignore that until we get further along in the lecture. But good question. Any other questions? Yeah.
So if we really do only have one processor, we start running it, and we load up the instructions.
Yep.
Does that mean that we have to decide when we start executing that thread beforehand, when we're going to switch context, in the context of that?
So good question. So the question here is, when we start running, do we have to decide in advance once we start running, before we start running the pink one, when we're going to start running the blue one, is what you're asking essentially. Kind of, all right? We're going to take what's called a timer interrupt, which we'll get to in a second, which will take care of that. But suffice it to say that there's a little buzzer that goes off. Time, 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 and we keep switching. Okay? Good question. So what triggers the switch? So things like a timer is exactly right. There's also an interesting concept here of a voluntary yield, where the pink CPU basically, I guess it's fuchsia instead of pink, fuchsia CPU basically says, all right, I don't need the processor anymore, go ahead, give it to somebody else. Okay, that's a voluntary yield. Okay, and some languages actually give you yield as a primitive. And then also, anytime you do I/O, so if the fuchsia one, pink is so much easier to say, tries to do some I/O to a disk drive and it's going to take a long time, the operating system will say, well, I can't do anything with you. You're going to go to sleep. Let's pick up blue. Okay? So there's lots of reasons for switches, and we're going to learn more about them as we go on with the operating system. But the timer will be our primary one today. Yeah, question?
Do you manually override like multiple programs like this? Like you want to have your CPU all work on the left?
So this question, you mean could the pink one decide to ask for more CPU time than it was supposed to?
Could the user say like I'm a super user, so I'm going to say I want my this program to use all of it?
Sure. So basically, essentially we have scheduling priorities. We're going to get into interesting scheduling a little later in the term, but scheduling priorities you can set, especially if you're a super user, to give most of the CPU to a given thread. Yes. Question?
Is the sleep function considered a voluntary yield?
Yeah, sleep is a voluntary yield. Yes?
So, yeah, is there a way for a process to sort of ask for more instead of like a super user doing it? Is there a way for a process to sort of say, I want any more processing?
Yeah, so processes that are not the super user are allowed to ask for priority under some circumstances. It depends a lot on what the security model is and whether they're allowed to do that or not. Because you can imagine that a process that was errant and was a virus or something could say, I want all of the CPU, right? Or I want 110% of the CPU, and that's now a denial of service capabilities. You've got to be very careful about what you give out. Good question. Yeah, go ahead.
Is it possible to run it sequentially if we want to, like each of the threads?
That's a good question. So could we run these sequentially? So the answer is certainly yes. But if you ran the pink one to completion and then the blue one and then the yellow one, you'll have no you'll have no illusion that there's more than one processor, especially if the pink one is computing, say, the last digit of pi. I would say blue and yellow are going to be very disappointed. Okay, so the thing that the timer provides for us, last digit of pi is 5, by the way, in case you guys weren't aware of it. I'm kidding. So, guys were like looking at me like, what? Really? So, anyway, so this idea of different scheduling algorithms is going to be some interesting lecturing we're going to do a little later in the term, where we're going to talk about different ways of doing it. What you've basically suggested here is what used to be called batch processing. And back in the day, when the big machine was the thing that we had to worry about, and those humans were pesky and somehow, wasted cycles on the big machine, batch processing was often the best way to get the most efficient use. It's not a good way to get humans that are happy, because you could have whoever's blue here is now going to be very blue because pink is computing the last digit of pi. So that's an issue. Okay? But yes, I would say that notion of batch processing, that's a scheduling decision. And so, good. So you start to see, we haven't really done anything too complicated with the slides, but you can start to see the space of things you can do in operating systems. So scheduling is an amazingly interesting topic. If you feel like you want to look at it and look ahead, there's a whole chapter on scheduling. I don't remember which one it is, but it's in your book, and it's an interesting one. And when we start talking about real-time scheduling so that the blue one, say the blue one is the brakes of your car, we better make sure blue runs well and quickly, right? Because otherwise, if pink is busy computing the last digit of pi, you just hit the wall without stopping your car, right? Okay, good. So let's move on a little bit. So the basic problem of concurrency here, there are many of them. It's going to lead into scheduling. But the basic problem is, suppose we only have a single CPU, a single DRAM, a single I/O devices, and so on, one of each. How do we make the processes or the things that are running think they have exclusive access? And the OS has to coordinate all of this, okay? And it's got to make sure that we can handle multiple processes at the same time, I/O interrupts and so on. And the question is sort of, how does it keep it straight? All right? And the basic idea is going to be to provide a virtual machine abstraction, which is a very simple abstraction for processes that make them think they've got the whole machine to themselves. And we'll clean it up under the covers so they don't know the difference. All right? That's going to be our strategy. We're going to fake it out so they think they have the whole machine, and we're going to fake it out under the covers so that they can continue believing they have the whole machine, except for maybe it's a little slower than they were expecting. All right? And Dijkstra actually did this for the system. You have confidence when you call yourself, I'm going to build the system. Right? And Dijkstra had a lot of confidence. But his first sort of multi-threading version of this had a few thousand lines, and OS 360, which was in the 60s, basically had over 1 million lines. So in the span of a decade or so, we suddenly went from a few thousand lines to 1 million lines. And of course, what was kind of interesting about OS 360, this was on the IBM machines, it was released with 1,000 APARs, or anomalous program reports. It was released that way. Well, they knew they had 1,000 bugs they didn't understand, but they released it anyway. And so that's only gone downhill from there. Okay. All right. So the properties of this very simple technique we've been talking about is all virtual CPUs share sort of the non-virtual resources. So all of the I/O devices are the same. The memory is the same. And the consequences of doing this is each thread that's running can access the data of every other thread. Because all we're doing is just kind of switching one out, switching the next one in. We're not doing anything with the memory. Okay, that memory's there. Thread number 1 has its memory. Thread number 2 has its memory. They're in the same address space. No problem. Okay, except when you care about things like threads overwriting the operating system or threads overwriting data from another program. Okay, so you can start to see why this is very simple, but it's not really what we want in the grand scheme of things. Okay? And by the way, this unprotected model was very popular up until about 2000 or so. So embedded applications still tend to do this kind of multiplexing. All the early Windows and Macintosh machines all kind of shared the same address space. And The only way you got multi-threading was a given process you couldn't even call it a process, a given thing that was running had to decide to yield frequently enough that all the other ones got some CPU time. So it's very common to get this crash. Macintoshes did this a lot, where you had programs that were running and all of a sudden everything stops, and it's because one of them decided to compute the last digit of pi. Okay, this was very, very common in the early 2000s before they figured out it would take a while. So I'm kidding then too. But so this idea of having to yield in order to make multi-threading work was actually a common technique, and we can see that that's not a very good one. Okay. Questions? So we got to do something. I mean, what are we going to do here to fix some of these problems? How do we protect? Okay, so maybe software is checking what, though?
Checking the memory space.
So the software, so what software, first of all? So the operating system has to somehow check the memory space. So how's that going to work? Okay, so the only problem with having an operating system do that, for instance, as you suggest, is if you're ever going to give the hardware over to a given thread, by the time the operating system takes control back and notices, something bad has happened. Because the little interesting issue that I didn't bring up before was I talked about pink and blue and yellow, but there's red in there somewhere, which is the operating system. And so since there's only one CPU, the operating system isn't running when programs are running. Okay? Sometimes this is compared to an insane asylum where the inmates and the people in charge are all the same, right? Okay, so you got to factor the operating system in. It's a good thought, but it's a little tricky, right? Because when something's running, the operating system's not running. So that's interesting. What else can we do? Yeah.
To adjust the memory references in the instructions of the other program before you let it run.
Yeah, so somehow we're going to have to do some adjustments to make sure that programs can't overwrite other programs or the operating system. So we're going to pull some hardware into this picture. Good thought, okay? So let's now bring out the process, which is the title of this lecture. Okay, and what is a process? A process is an execution environment with restricted writes. It's basically an address space with one or more threads running in it. It completely owns a chunk of memory. It owns file descriptors, file system context, etc. It's encapsulated. One or more threads are encapsulated within a process. And more importantly, each process is protected from the other one. So the address space, just hinging on that previous answer, that address space of one process is completely different than the address space of the other one, so that even if process 1 tried to overwrite process 2's, the address spaces are different physical memory and it's impossible. Okay, so what we want to do is we want to arrange so it's not possible for one process to mess up the memory of another one. Now notice, by the way, I did slide something in here, which is subtle, but I wanted to point it out. I said that a process is an address space with one or more threads in it. So we're actually allowing there to be multiple threads in a given address space. Okay, so one way you could look at this picture I had earlier is that if we're doing this kind of very simple switching, this could be like all of these are part of the same process. So a given program has a bunch of threads in it, and they all share the same memory, but there's another process that looks exactly like this, and those two are not able to interfere with each other. Okay, so I'm starting to group things together. And by the way, by the end of the term, you're easily going to understand what that means, because you're going to have started designing programs whose processes loaded into memory have multiple threads inside of them. That's a very common thing. Very common. Simplest one to think about for you guys now is a web browser, a web server. Okay, the web server is running in a process. Lots of requests come in. Each request potentially is given to a different thread. All the threads are cooperating to provide that website. Okay? But they're protected from other things running on that same server, like the mail daemon or whatever. Okay. Just mull over that for a little bit. Now, so we have processes, and an application then consists of one or more processes. So there's lots of levels of parallelism in here. We debated at various times when we talk about course restructuring and so on in the department, how important is parallelism? Should we teach you guys parallelism from 61A on up? Okay, and you've noticed probably that there's starting to get more and more parallelism in there. Okay, and the parallelism that you mostly run into before this class is all of the form threads in a single process. That's the way to think about what you've been doing up till now. And we're now going to put the protection boundary and call it a process and allow multiple processes to be in the same processor. Okay? Now, so we need protection. How do we protect a process from another one? So first of all, the operating system, I said this, but I want to say it again, must protect itself from user programs, because if you have a user program that's running and it screws up the operating system, then all bets are off. Okay, your credit card at Target is toast. It's somewhere else. Okay? I don't have anything against Target, by the way. I like Target. The operating system needs to protect itself for lots of reasons, but not just security. Look at some other ones I got there. Reliability. If user processes happen to be buggy, they're going to screw up. And if they can screw up the operating system when they crash, they've just screwed everything else running up on that machine just because there was a bug. That's a non-malicious instability caused by bugs. Think about that, right? If how many people have never written a buggy program before? Oh, I'm just kidding. Oh, there's one up there. Okay, good. You available for consulting after class? Okay, so you need to have protection just to make sure that programs don't crash the operating system by accident, right? We also talk about privacy, right? That's important. If one process has gotten your private data and another one can snoop on it, you've just lost your social security number or your credit card numbers or whatever. Okay, and then also finally fairness. This came up in the scheduling question. We have to make sure that basically each process gets its fair share of the operating system, of the time on the processor. It's got to protect user programs from one another. And the primary mechanism that we're going to talk about after we take a little bit of a break here is limiting translation from program address space to physical memory from one process to another so that the two of them don't overlap. Okay. And we have a bunch of other mechanisms that are going to be interesting, like privileged instructions, I/O instructions, special registers, and so on, that will help us protect overall. Okay. Now, let me just see what helps do. Okay. Let's pause for just a second. I'm going to take about a 3-minute break. Stand up, stretch, turn around, say hello to your neighbor, take in a deep breath.
Seen a stenograph?
I've seen them in courtrooms. But is that similar idea?
It's the same thing.
Cool.
I know of a programmer who's very interested in my stenography because they're starting to use it for programming because it's all in code.
Sure.
Pretty much shorthand.
It's better, yeah.
Write codes really fast. And I was just wondering if you knew anything about that.
I don't know if that makes a lot of sense to me. I mean, people that program a lot tend to get carpal tunnel problems a lot. That's where the nerves.
Yeah, I know what it is.
So I can imagine that with coding, you sort of have less stress because you're sort of doing less for a given amount.
Right. Interesting. Huh. Yeah.
Makes perfect sense to me. Sorry about the slides. I did get them up an hour before, but I'm going to try to get them up a day.
Well, there's not too many unique data points except the dist something you said. Dist. It's like DYSTRIST or something.
Oh, distribution? Destroy off the
What is that technical term?
Oh, okay.
I don't know. That's fine. I spelled it out really
Okay, good.
fast.
That's cool. Okay, everybody start sitting down. All right. Whew. Now your attention span just went way up again, right? So the fourth concept I promised you for today is dual mode operation. And I just want to say a little bit about this. So this is the hardware itself on typical processors today. Provide at least two modes, kernel mode and user mode. Okay, so kernel mode is the mode in which basically everything is fair game and the operating system runs in kernel mode. User mode is going to be the mode that processes run in, and they're with restricted privileges. Okay, and what do you really need to support dual mode? Well, obviously, a bit. Okay, it's either 0 or 1. But that's not too interesting yet, right? But certain operations or actions that the processor can do are only available in kernel mode. Okay, and I'm going to give you a good example of that, which is changing translations in a second. And the user to kernel transition sets the bit and saves the user PC. And the kernel to user transition clears the bit and restores the PC. And so if you notice, clearly we're going to have to talk about how do we go from user to kernel and how do we go from kernel to user. And the other thing to note is the user to kernel mode is the thing we got to be very careful about how we allow it. Right? We don't want to let the user mode program arbitrarily go into the kernel, because if it arbitrarily can do anything it wants, then why bother having protection? Okay, so it's kind of the best way to think of this is you're at a concert or an airport. There is a very narrow path into the restricted space, right? And so that everything can be checked to make sure that when you go through that space, you're doing what you're supposed to. Okay, and that's going to be how we're going to be very careful with our, some people call these call gates, depending on what you're talking about, but ways into the kernel have to be restricted. Ways out of the kernel are not, because the kernel has all power anyway, and so if it wants to screw things up, you're basically in trouble anyway. So we don't worry about the kernel going the other direction. We do worry a lot about the user going into the kernel. And so, here's a picture from your optional book. This is from the Dinosaur book. It shows a typical Unix system where we have user mode and kernel mode and hardware are the three pieces you see here. And user mode is the restricted commands that don't have full privileges, and typically applications run up here. Libraries like shells and commands and so on run up here. Kernel mode is the most powerful aspect of a system, and this is where all of the secure things happen. This is where the scheduling happens. This is where file systems are built and so on. And then the hardware, of course, is the actual hardware. And what I want to point out is you can see this fact that there are two modes leads to an obvious division of operating system code into, of code into those things running at user mode, those things running in kernel mode. This is not the only way to organize an operating system, and when we get a little further into the term, I'm going to tell you some things about like microkernels and a few other organizations, but this is a good one to start with. Okay, and in this, in order to go from user mode to kernel mode, we have to do something very specific, careful, and then going the other direction, we just let the kernel restore. And so we often think of the kernel this way, where the hardware is this, the bricks. The kernel mode is the special protected code that's specialized. User mode is everything else. And by showing the kernel at the core here, I'm kind of stating two things. One, it's smaller. It's at the center of everything. I guess I'm saying three things. And the other thing is, because it's smaller, it's hopefully better debugged and audited. Right? So the idea is hopefully the thing at the center, somebody spent a lot more time looking at than the code that's running on the outside. And so we're going to make sure that when we get into the red portion, we're executing code that has been vetted very well and gone through a lot of debugging, whereas the user mode code is basically the best stuff you can write but we're not going to trust you to be perfect. Okay? And when we talk about the Windows distribution or the Linux distribution, there's always a kernel, which is this part in red. And of course, how do we run a program? Well, we're going to go do an exec call from the kernel out to user mode, and then the user mode program will eventually exit, get us back to kernel mode. So everything's centered at kernel. The user might try to do something like open a file or a socket. We're going to talk about all these things starting next time as well. But they make a system call, which is a controlled gate into the kernel. And then a return from the system call goes back to user level. So when you make a file system read call, you take a sys call, and then the return comes back out. Okay? An interrupt is a good example where some hardware down here says, I need service. The user mode code never even learns about that directly. What happens is an interrupt causes you to go to kernel mode. The kernel mode handles the interrupt, deals with the hardware finishes, you got some stuff going on, and then eventually we return from interrupt, that's what RFI stands for here, and the user mode sort of blithely keeps going as if nothing happened. Okay? And then finally, user mode exceptions. A good example of this is you try to divide by 0, we go into the kernel. Okay, questions? All right. So now that we have this idea of dual mode, let's see what we can do about our protection question. So notice that we have very controlled access into kernel mode, and kernel mode is that special setting of the bit that says I can do anything I want with the hardware, whereas when I'm a user mode, I'm restricted in what I can do. And the question you might ask yourself is, with that distinction between full access and restricted access, what type of restrictions help me out in making processes stable? And so here's an interesting restriction. So let's talk about this. This is a what's called a basin-bound style protection, B&B. It's not bed and breakfast, okay? I know you're all hungry. But so the idea is there is a base register and a bound register, and the base register says this current thing that's running is not allowed to have any access to memory below the base. And the bound register says this thing running is not allowed to access anything above the bound. So we have this big chunk of memory, but by putting a base and bound on it, we can restrict what the CPU is allowed to access for memory. And now all we have to do is just move those base and bounds around as we're multiplexing to give us the illusion that we're multi-threading and to protect different threads from each other, or different processes from each other. Okay, is everybody with me? Now, the downside of this, of course, is, what is the downside of this? Oh, and by the way, before you answer that, hold that 1 second. I do want to point out, when we're running in the kernel can change the base and bound registers, okay? And we're not running in the kernel, the user code can't change the base and bound registers. Everybody with me on that? I forgot to say that rather crucial little point. That's what our protection has. So what's the downside of this? Yeah? You don't have the illusion of unlimited space. Good. And what's worse is you don't even have the illusion that you have 0. Right? Because this program has to be relocated so that it starts running at 10000, not 0. And if I run 2 of the same program at the same time, each of them has to be relocated differently in order to work. Okay? So this is another party, thing you can say, wow, did you realize how important it is to have 0? I learned that today. Okay? Everybody wants 0. All right? So this doesn't give you 0. Everybody with me on that? How can we get 0 out of this? Yeah. Okay, how do we virtualize it? What? Oh, good answer. Yeah. Page table. Great, but too complicated. We'll get there in a second. Something simpler. Hold that answer for a little bit. Yeah.
Can't you map the addresses to 0 through whatever?
How would we do that? What's the simplest thing you could come up with that will do this? Yeah. Yes. What if we take the program address that the CPU has and add the base to it, and that will give us the actual physical memory address? Okay, so a way to look at this is basically we're going to take things coming out of the processor, which we're going to call virtual addresses. We're going to send them through a translator to the physical addresses. And the simple thing that you can see that we just suggested is this. Instead of checking to be above or below the base, what we do is we take the program address and we add the base to it. And that now gives us the actual starting point in physical memory. And, by the way, the bound is checked for all the program addresses to make sure they're not above 0, 1, da-da-dump. And if they are, we fault. Otherwise, we go ahead and allow the access to go through. Okay, do you see the really subtle thing I did? I put an adder in there. And now, voila, the programs get to have 0. Because what is 0? Well, with this base and bound, 0 is 1, 0, 0, 0, 0. And when we set the base and bound for the next thing that's running, 0 maps to something else, because 0 plus something else is something else. Okay, that's another profound thing you learned today, right? Questions? Everybody with me? This, by the way, harkens back to the Cray 1. So this was one of the first things that Cray did when he built his supercomputer was he had base and bound style protection. Simple. Okay? Now, let's take a look at how to tie this all together. So by the way, we're going to forget whether we have comparators or adders in there. That's going to be a small detail we'll worry about later. But now let's say if we have some sort of base and bound, what do we do with it? So let's suppose the operating system is going to load a process. So here we're busy running in the operating system. Notice that the system mode is kernel mode. That's why it's red and 1. And the program counter is busy up here in operating system land running some stuff. And what it's going to do is it's going to load, let's say, this yellow thing into memory. And it's loading it, and it's setting up a special register, which is going to be the user PC or the return from PC or whatever to point to the beginning of the code. And it's going to set up the stack pointer to point at the end of the stack space. And we're still running in kernel mode, but we're going to run a special instruction called return to user. And what is that going to do? Return to user is going to atomically switch the system mode from 1 to 0. It's going to load that user PC into the PC, and it's going to say go and start running. Ready? Okay. Poof. Okay, that one instruction, notice what it did. It loaded this special micro PC register or user PC into the PC and set, because it's system mode 0, the base and bound are now operational, and suddenly we're running in a protected space in user mode. Let me go back. Everybody see that? Ready? Here we go. 1, 2, 3. All right? See? So notice the operating system set it up, ready to go. Set up the base and bound, set up the PC to return to, and then the last instruction it hit was return to user, and now we're running in a protected space. And this user code, because it's running in user mode, isn't able to do anything else. It's stuck in here to only reading and writing in that spot until it executes something, until there's an interrupt, until there's a system call, until one of those controlled gates back into the kernel turns system mode back on for us. Okay? Very simple hardware. Okay? So how do we return to the system? So let's look. So we have 3 types of transfer I've mentioned. There's system calls, which is process request for system service, like file system calls or exit or whatever. We can have an interrupt, which is something coming in from the outside, like a timer interrupt or an I/O device saying, hey, there's a network packet available. Or we could have a trap or an exception we divided by 0. Okay, and actually in your book, which is pretty good reading, by the way, they talk about lots of uses of exceptions that are kind of interesting, including emulating instructions you don't actually have. You can do that with exceptions. Just put in a bad instruction code, and when the exception happens, the operating system transparently pretends that you had that and runs the registers like if you did have it, and then returns from exception, and you never know the difference in the user code. Okay, questions? So let me show you an example here. All 3 are unprogrammed control transfers. So the question you might ask is, well, how do we get the gate aspect I just mentioned, control into the kernel? And the answer is, for instance, with interrupts, there's typically a portion of the memory that's in the operating system called the interrupt vector. And that interrupt vector takes the type of interrupt, like for instance, it's the timer interrupt, and that timer interrupt in hardware causes the processor to look up an address of an interrupt handler in the operating system and start executing there. Okay, and all of these other things might include what happens when there's a divide by zero, what happens when a network interrupt comes in. All of these different interrupts are really just pointers to code in the operating system with a slight little bit of hardware where, gee, when that happens, we transfer into system mode and save where we were and then go jump to this handler. Okay. So for instance, here, we're running along. The timer interrupt's going to go off because yellow code is done enough. What happens? The timer interrupt happens. And look at what we did here. Ready? Poof. Everybody see this? Okay. Poof. Okay. Now what did that just do? What it did was it copied the PC that was running into the user PC and set the PC program counter to point into the kernel. And this thing that it looked up was based on whatever interrupt actually occurred. It decides where to go in the operating system. And now it can handle that timer interrupt. And what might happen with the timer interrupt is it says, oh, yellow is done. Let's do something else. Okay, and notice that there's only a select set of things that are saved here. We actually save the program counter. We save a couple of things that the operating system would definitely screw up if you started running the operating system. But we don't save anything else, and it's up to the operating system to save the registers and all that other state of that process in order to make sure that you can return to it later. So if we're running a timer interrupt, notice what happens here. The timer interrupt code might actually save the whole set of registers into a little chunk of operating system memory, the yellow chunk over there, and says, okay, well, when I want to come back to yellow, here's all the stuff I need. And similarly, load up the green back into the processor. And notice how now our PC is pointing somewhere in the green code. Our registers are the registers that were running the last time the green code was running. There's a new base and bound. And then we do a return from interrupt. So notice this is stored in the static data of the operating system. We do a return from interrupt, and poof, now we're running green. And we're doing so in a protected form. Okay? And I just did a protected control transfer for you guys. Everybody with me? And if that timer interrupt happens on a regular basis, then we can keep swapping back and forth between these different threads. And we've protected things. So green can't mess up yellow, yellow can't mess up green, neither of them can mess up gray. And we're all happy. At least I'm happy. I don't know about you guys. You're all happy, right? Okay. Question. Yeah.
So when you switch processes, do they override the OS memory, or do they have their own space?
Say that again? Oh, I see. So there's the static, you're talking about the static data inside the kernel. For every process that's loaded in that you get with, say, PS, AUX, or whatever, every process has its own process structure that's set aside. And when that process is finally killed off, then the process structure goes away. But until then, it's got a unique thing called the process control block, basically, that holds on to that. That answer that question? Yeah, go ahead.
So it makes sense that the base is translated, but how is the bound enforced, and who enforces it?
So the bound is enforced by the hardware, and it basically says if that address is above the bound, I cause an exception, which causes you to throw the process out. Question in the back.
When you do something that's like killing the process as opposed to interrupting it,
Yep.
does it do a similar set of steps, or is there a much more simple, just like kill it, get all the registers and everything?
Well, it starts out the same way, and then it basically throws everything out. But yeah, that's a good question. When you kill the process, what happens? Yeah. Okay, so what's wrong with this very simplistic translation? Now that we've got basic protection, can anybody see a big flaw here? Yeah.
If we allocate some space that was previously used by another program, we don't keep track of how far our stack and our heap have overwritten yet. We could have access, like we just say that we have all this space in the middle. If we left that big gap in the middle, we have overwritten or anything.
Okay, that's a very interesting and more advanced answer to my question. Yeah, so we haven't talked at all about privacy. Clearly, when you start a new process, you got to make sure all the memory is zeroed. right? From the previous part. That's a good question. There's actually keep that one for a little bit, another lecture or two, but that's a good point. So are there any other interesting problems with this? Yeah. Why? Yeah, so if you look at this, we don't, notice how we've got, so the point was that we're allocating too much space and we're doing so inefficiently. We want the heap and the stack to be able to grow, and we want that hole. Remember I mentioned the hole in the middle? But we got to allocate more space than we could possibly need so that we don't have the two sides of the stack and the heap run into each other. So the problem with base and bound is it doesn't give you a good way to deal with the hole. All right, now let me first very quickly say what x86 does. x86, which is probably what a lot of you guys are running, has a whole series of what are called segments, and each segment is its own base and bound. And so there is a code segment and a stack segment and a heap segment or whatever. So each segment gets a chunk of memory, so that's kind of nice. Okay, takes care of the problem with the hole. And then finally, there's lots of other interesting things, and I just wanted to throw this up before we completely run out of time, which we kind of have. But this, we're going to get to a little bit later in the term, but this is what's typically called paging. And what you see here is that each process, number 1 and number 2, go through a translation table to point at individual pages in the main memory. And so notice how the blue and the green are kept separate from each other simply because blue's code segment goes through a translation and points to a completely different place in memory than green's does. And it's up to the operating system to load those translation tables. But if we set it up right, we can set it up so that blue and green never interact with each other, and we don't get any protection problems. And furthermore, other major problem with what you just saw with base and bound, which you should think about that a little bit, is if I want to share between two processes, I would have to somehow overlap their base and bounds or something goofy, right? By having separate segments or pages, we can have some of them overlap, most of them not, and now we have a happy medium between protection and communication. Okay, so let's end there. So in conclusion, we talked about 4 fundamental concepts today. We talked about the thread, which was a single unique execution context. Got a program counter, registers, execution flags, its own stack. We talked about the address space, and we also threw in translation now, which is what we really want to make this work well, and that base and bound using the adder is there. We talked about processes, which are protected groups of an address space plus threads, and then we talked about dual mode operation and protection. And so now you guys are going to be having a great time at your party tonight. Keep in mind, the last digit of pi is 5. I'll see you guys on Wednesday. Do homework 0. Start sooner rather than later.